Hi, this is another video about the colligative properties of solutions. You've already watched a video about how vapor pressure is lowered by the presence of a solute into a solvent, how boiling points are elevated by the presence of a solute in a solvent, and this video is going to look at freezing points. So the definition of a freezing point is just the temperature at which you first start seeing crystals appearing in a solvent. And so let's go ahead and look at another animation of how a freezing point and we're going to go ahead and use water. We're going to see how the freezing point of water is affected by the presence of, and we'll use sodium chloride here. And we are going to add quite a bit, and let's go ahead and we are dumping the sodium chloride into the water, and then it's going into this cold water tank. Now, water will freeze when it's pure water at 0 degrees Celsius, and now we're seeing what the effect of putting some salt in there will do to the freezing point. So let's see what's going on at the molecular level. See these little orange spheres? Those are the solute particles, the sodium and the chloride, and we see that these blue solvent particles are trying to get organized and form a solid. Okay, well, what happened to the freezing point? It is now negative 2.27 degrees Celsius. So the freezing point went down. And so we call this the freezing point depression. Remember, our boiling points went up, so it's boiling point elevation. The freezing points go down. It's called a freezing point depression. So the presence of a solute will make the freezing point of a solvent go down. Can you think of any practical uses of this, possibly that we use in the wintertime on the roads in North Carolina? Yeah, when they put that brine on the roads, that's, a salt. And so they're adding the salt to the road so that the freezing point of the water, or the liquid precipitation that we get, will be lower than 32 degrees Fahrenheit or 0 degrees Celsius. So very practical. All right, well, let's go ahead and summarize. Freezing points are decreased with the presence of a solute, and just like with boiling points and with vapor pressure, if you add more particles, it will decrease the freezing point even more. All right, so here's some qualitative questions. Which will have the lowest freezing point? They all have the same concentration, so now we're looking for which one separates into the most number of particles. They're all the same concentration, so you might think, oh, they're all the same. That would be true, except this does not separate into particles, so that Van 't Hoff factor is 1. This separates into 2 sodium ions and 1 sulfate ion, so that would be a 3, and this separates into 2, a sodium ion and a chloride ion. And so the one that would have the lowest freezing point would be B here, because it has the highest number of particles. But then we could say, well, let's all have I be the same. So sodium chloride will separate into 2 particles. So that's all the same, but what's different here is we have different concentrations. The lowest freezing point would go to the one that has the highest concentration, because you would have the most particles in that. And now here we've mixed it up. We have different concentrations, and we have different I factors. This is 2, this is 1, because it's molecular, and this is 3. And then the different concentrations. So 2 times 0.25 gives me 0.5. 1 and 0.45 gives me 0.45. And 3 times 0.2 gives me 0.6. And so this is an example where, even though it has the lowest concentration, because it separates into the most number of particles, it will actually have the lowest freezing point. Had we been asking for the highest boiling point, it would have had the highest boiling point. If we had asked about the vapor pressure, it would have had the lowest vapor pressure. So we have the most particles in this 0.2 molar calcium chloride solution. Okay, so That is qualitatively. You can guess which one will be the highest or the lowest or whatever. But now let's get quantitative. How much exactly will the solute lower the freezing point? And there's an equation for that. How much the freezing point is lowered is equal to I, that Van Hoff factor, the number of particles. And then there is a constant, which is specific for the solvent that you will always be given, times molality. All right, we learned, doesn't this look really familiar from the boiling point elevation? This is a constant for, it's a freezing point depression constant, and it is unique for each solvent, and you'd be given a table or the constant, and this is molality. Do you remember what that is? Molality is moles of solute divided by kilograms of solvent. Okay, so again, we use molality here because neither one of these units is affected by temperature, and it's exactly like the boiling point elevation formula, except once we calculate our change in temperature, we are going to subtract that from the normal freezing point because the freezing point is lowered. Okay, here are some examples of the KF values for different solvents. So let's go ahead and we're gonna, in the next slide, I think we're gonna work with water where the KF is 1.86. All right, we got 100 grams of water and we've got 8.5 grams of this molecular solid here. So I is 1. That's molecular, it's not going to separate. We said that the KF of water was 1.86. And then we have to get the molality. And from our video on boiling point elevations, we had 8.5 grams of C12H22O11, and that corresponded into 0.0248 moles of, so let's see, of C12H22O11. You can go ahead and calculate the molar mass of this and take 8.5 and divide by the molar mass. You should get that value. And we are going to divide by kilograms of water, which is 0.1 kilograms. And so our molality is the same as we calculated in our last video, 0.248. And so our freezing point will go down by 1 times 0.248 molal times 1.86 degrees C per molal. And my answer that I get is 0.461. So what is the freezing point of this solution? Water normally freezes at 0. It has now gone down by 0.461. How much did our temperature change? And we know that freezing points go down. So our new freezing point is negative 0.461. The freezing point was lowered by the presence of a solute. All right, so I just want you to know that we're not always dealing with water. Here we would, in this particular question, we are dealing with a different solvent, and our solvent here would be chloroform. And so we would have just a different freezing point of the pure solvent and a different boiling point and different KBs and KFs, but the process is exactly the same. So let's go ahead and just kind of practice some things here. Increasing boiling point. Okay, here we go. Glucose is a molecular solid, so I is 1, and the concentration is 0.12, 0.12, that's a 1. Okay, 0.05, I is 2, times 0.15, I'm sorry, 2 times 0.05 is equal to 0.1. And then zinc nitrate will, the nitrate stays together, it will ionize into 3 particles, times 0.05 is going to give us 0.150. This will have the highest boiling point. This would have the lowest. So increasing boiling point, it would be the lithium bromide would have the lowest, and then the glucose, and the highest boiling point would be the zinc nitrate. All right, so in conclusion, solute particles will have the following effects on the physical properties of a solvent. Solute particles will decrease, there we go. Let's see, sorry about that. Solute particles will decrease the vapor pressure. What do they do to the boiling points? They will increase the boiling point, and solute particles will decrease the freezing point. Okay, now, where do we go from here? Well, we can use this data to figure out the molar mass of the solute that we're adding, and those are some pretty cool labs. All right, well, I hope you have a good understanding of colligative properties and how solutes will affect these physical properties of solvents. Thanks for watching.